So now let's welcome Eldad to give his oral presentation on Tango Graph Neurodynamics via learned energy and tangible flows.
Thank you. First, I want to thank anyone who actually managed to make it this morning. It's a little bit early, but thank you for waking up for this. Hopefully, I'll keep you awake for this time. It's joint work. Moshe actually came with the idea and run most of the experiments, and Carola is one of the authors as well. And I'll talk a bit about, again, graph neural networks. To the mic, okay. YouTube, okay. Streaming likes mics, but it's their problem. They did not come. Okay. So yeah, so I'll talk about this idea of how to improve over the standard flow that we do with Node and do. Okay, so what is the challenges that we actually have? The challenges when we are running a lot of these codes that we have today is we have vanishing gradients. This is everybody seen this kind of behavior when they try to train some things. Over smoothing, for some reason, people think still it's a problem. It's not really a problem. There are many, many ways to solve it. But if you just run off the box GNN, you'll find out that it's over smoothing. Again, there are many, many different ways to solve it. It shouldn't be a problem anymore, but people still think for some reason that's a problem. And again, just standard GNN will present something like this. The more interesting thing is over squashing, which I'll talk a little bit more about. Over squashing really comes when you have, for example, two big clusters and there is only a small way to pass from one cluster to another. Then you see that it takes a long time to pass information from one side to the other side, and that would be the over-squashing problem. So the hypothesis we have is that the current approaches, they're basically using some kind of diffusion mechanism. They rely on simple energy functions. Typically, it's the Dirichlet energy function people use, and that's what causing part of the problem. And one of the things you can do is you can derive a specific energy function, task-given energy function. So if you think about the Dirichlet energy function, it's generic. It's not task-specific. This is going to be specific energy function that belongs to the task that you want to really apply. And then you have to also take a dynamics that is going to be a little bit better than the standard stochastic dynamic. If you combine both of those things, we can solve some of these problems that we are actually talking about. And that's what I'm going to try to show you in 5-6 minutes that I'm going to talk about. Okay, so here is maybe an illustration and where we know this is coming. Very well-known function. This is called the banana function in some places because it kind of looks like a banana. And again, it's a very ill condition, at least in one direction. This is very typical. What happens when you have something like this in one direction? Even if you have the energy correct, you can still converge very slowly for this directional function. And because the conditioning is actually very bad, and we'll show something about it. So again, one of the things is if you can learn a better energy function, you may improve A, conditioning, B, you can actually converge faster if you actually take more direction to the whole thing. So we're going to try to do that, and without actually I'll see what we're going to do here. What we're going to do is we're going to really have two steps, and I'm going to talk first about the two steps separately. So the first thing is just want to learn an energy function. So you can think about a neural network that basically gives you an energy function. This by itself is being recently applied to many different fields. There are a lot of people that are looking right now at different energy functions. There are some papers that actually try to see what the best energy function would be for different things. And the idea, generally speaking, is that if you have a low energy configuration, that corresponds to basically good states. Yesterday, there was an interesting talk about physics-based, and it's exactly the same thing. If you think about molecular dynamics, for example, you would say the solution should lie in places that the energy generally stays very low. Here, you don't have an energy, so in molecular dynamics, you may have an energy that you know from physics. For many of the tasks that we actually have, there is no energy, given energy. Nobody knows what the energy for Cora or for any other data set, so you're going to learn an energy function that will do something good for you. And then the first thing that comes to mind is you say, okay, if I'm having an energy function, I'm going to move towards to descend towards the energy. Now I'm going to really take my chances and try this. Yes. So the energy going down will be basically the green thing that goes down. And as you can see from this picture, going down the energy is okay, but it can take actually quite a lot of time, so that can be slow due to conditioning. So learning an energy is not enough because the gradient descent may actually be very very bad, which means, by the way, if you're doing this as a, you think about this as a neural network, you'll need many, 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 many layers. Yes, bigger, higher, okay. You'll need many, many, many layers, and these many layers may actually make the thing not very practical in terms of actually working with the method. So the standard pictures that people show when they, well, we show this when we teach steepest descent in optimization, that you're here, you're going down, well, you're going orthogonal to the lines, and you may go up and down, you zigzag your way through, and that may take you a long time to converge. So that's the first problem. Let's say, okay, I construct an energy function, but still I go very slowly. What do we do in optimization? Well, we take another direction. We say, let's not take a single direction towards the optimization. Let's take a different direction that is going to improve over the first one. Typical thing that happens is we take, for example, the conjugate gradient direction. Okay, that's one option. But conjugate gradient, again, is generic. It's not problem dependent. What we decided to do is to do something a little bit different. We decided to take another direction, but to learn the direction for the whole thing. So we're going to take a direction that goes along the level set of the functions. We're going to basically take a second direction, and that's this one over here, the blue one, which is going to be orthogonal to the first direction, and combine the two directions in some optimal way. And these things is going to lead you closer towards the minimum. And that's basically the idea. Okay? So you combine these two directions, and now you get your flow that is based on A, the steepest descent, plus another direction, again, similar to algorithm optimization that use conjugate gradient or other things that concept. So again, this is the standard thing. What happens is that you have, again, first direction is just taking the gradient of the energy and having a line search basically, or step size that depends on, again, you're learning it as well. And the second one is tangential direction that basically is going to be orthogonal to this direction, also with a step size that is learnable. Okay. That's the basic idea. Now, a little bit of math. How do you do this kind of thing? Very simple. You construct an energy function, and you say, I'm taking the gradient of the energy function and a step. So that's this classical approach of taking a step. And now, if you think about what you're doing, you build an energy function, standard thing. You can actually go ahead and build it as a network, and eventually sum the whole thing square. The interesting thing is more about the tangential energy. What you have is you have another direction that you take, and then what you do is basically do a projection towards that, compared to that direction, and then you basically take the two together. So it's a very simple thing. Now, the important thing to remember, and maybe the pictures that I showed before are a little bit confusing if you take these two directions, that in 2 dimensions, there is basically a single orthogonal direction. Now, in infinite, or not infinite, 3 dimensions even, not to talk about n dimensions, there are infinite directions that will be orthogonal, okay? And now, if you're just using, again, conjugate gradient, for example, it's going to be orthogonal, not orthogonal, but it doesn't matter. I mean, the point is that if another direction in a set algorithm, the direction that you're going to use, the tangential direction, is going to be fixed. Here, we're going to learn which one out of these infinite many are going to be the best one to choose based on the task at hand. So based on the task, you're going to pick another direction that is going to be best one. And this is what really makes the whole thing converge much faster compared to a standard, let's say, conjugate gradient method, or something that just choose a priori without knowing anything about the task, choose another direction. Okay. As usual, when you do this kind of thing, it's pretty actually straightforward to prove a few things, because again, these are, when you have, the minute you have an energy, if you're a mathematician, the first thing that you have is, it's like nice, you can prove stuff when you have energy, at least locally, so you can, for example, prove that you have, that you're basically going down, or at least not going up. The second thing, which is actually more interesting, is because you have a tangential direction, you can prove that you can actually go, even when the energy is completely flat. So typically what happens in steepest descent, you go to a flat region, you can't go anywhere, right? You're stuck. With tangential flows, you can go even in areas when the function is completely flat, you can still go. So for people who are new in optimization should know that one of the biggest problems in optimization is not so much the multiple minimums, it's a problem by itself. One of the biggest challenges in optimization is when you get basically, we're here in Arizona, to the desert. I mean, it's all flat and there is nowhere to go. So you're stuck somewhere and you're just going slowly down, and basically it's a death for every optimization algorithm. So the tangential steps allows you to go in directions that are completely flat, relatively fast. And that's one of the nice things about the whole thing. That's what basically this theory shows you. And you can demonstrate it in this example, that again, you can go in some way to, if you're like here, you're going one direction is the orthogonal one. Of course, the steepest descent, the contours change very quickly. This is where you want to go in the steepest descent direction, but the second direction allow you to go in the valley actually quite fast because you're learning this kind of direction that allows you to go inside. Okay. To show why this is interesting is the standard over squashing problem. So in this case, you have, again, two clusters, cluster 1, cluster 2. You have a connection between them, so you have a bottleneck here, and you want to pass information from one side to the other side somehow. So if you look at standard flow, you'll have a hard time to move because you'll need to go over all these kind of things, and only then you can go to the other side. In what we have, you can go very quickly from one side to the other. Now, this is an explanation that I don't like so much. The way I like to look at it is to think about it in terms of eigenvalues. If you actually look at the eigenvalues of the Laplacian that you're going to get from here, you'll see that the eigenvalues are going to be, besides the 0 one, of course, you're going to get the Fiedler eigenvalue, which is 0.01, and then the one immediately after that is basically order of 100 times bigger. So this is very ill conditioning. It's exactly that situation that we talked about before. One direction that is very small, another direction that is kind of nice and large. And what happened when you are using basically a tangential flow, it takes one direction, the steepest descent direction, and then the second direction, it just finds the right thing and does and goes in the right space here. Okay, this is the slide I hate, but I guess at every machine learning conference, you have to have this kind of slide. Otherwise, nobody believes you that your method is good. So you have to show how you compare to every method that everybody else in the world that ever thought about it can work. So hope you make you happy. Okay, that's the whole thing. So yeah, I mean, you can go ahead and figure out that the method is actually reasonable and it's doing the right thing. That is fine, and you can compare it to many different methods. As usual, when you send a paper to somewhere, that's exactly what people ask you to show. So yes, it does compare very well to a lot of different methods, and that's not very surprising because, again, most of these methods have either fixed energy or fixed directions, so it's not that surprising. You can compare it to other tasks that people have looked at, other more serious sometimes, not sure more serious, but more larger data sets that people sometimes use. And you can look at heterophilic node classification, you can look at different type of things, and you can still see that the method performs very well, and actually in some cases dramatically well compared to different benchmarks that exist out there. And again, some of it is not so surprising. You have more degrees of freedom. If you have more degrees of freedom, expect to do a little bit better. Okay, at this point, that's more or less everything I have to say. So I just want to, again, take two take-home messages. One thing is that I think it's definitely worthwhile learning your energy function. This is something that is, to be honest, it's not, we're not discovering this in the ether. This is something that exists right now in many different fields, in many different problems in machine learning. People are now looking at how do you learn an energy function that is task-driven. There is a question, do you want to learn an energy function that is, I think yesterday was a good talk to hear about it. Do you want to discover an energy function that is generic for all tasks? Do you want to do a task-specific one? This is task-specific one, and there are some good questions about what do you want to do if you want to have a foundation model? How do you want to derive an energy for a foundation model? Not this talk, but it's a good question, and I think people should think about it. The second one is that when we have an energy, our first intuition is to go ahead and say, let's just use steepest descent. And that's like gradient flow, of course, have been there since the gradient flow. So it's a long time gradient flow. But the question is, should we continue just using gradient flow or move to a little bit more advanced techniques? There is a whole literature on learning to optimize. That people are looking at these kind of things as well. And the conclusion that we have, at least from here, is that learning a second direction on top of the first one makes a lot of sense, can increase convergence in this case towards the minimum that we want to go. So if you are actually thinking about deriving an energy, remember, energy is by itself maybe insufficient if you're not really allowing it. Nobody that is doing an optimization problem would say that they're converging after 15 iterations if they're using steepest descent. It just doesn't make any sense. If you ever taught any optimization course, first thing you know is that this is not converging after 15 iterations, even if you want to minimize, X transpose AX. So you need to do some heavier lifting if you want to converge. So if we are claiming we're doing an energy, and we are claiming you want to go towards the minimum and get closer towards the minimum, having something beyond just as steep as descent makes a lot of sense. Uh, this is it.
So there is one online question from Raffle. So he is asking whether functional is orthogonal with boundary conditions, which might be interesting with regard to the topic discussed here.
So I'm not sure what boundary condition here really means. I mean, we're talking about a network that have an energy unless again, we're not talking about a specific like bounded domain. So I'm not sure what boundary condition means here. You can think more about this whole thing as initial value problem, not a boundary value problem. But again, I'm not.
Thank you. So any other questions from the audience? Yeah.
I have two questions. First one is for your learned energy surface. Is there any kind of like scale consistency? So if I double the number of parameters, do I get a refined version of the energy surface that I had before? And then I guess the second question is, if I'm moving along tangential flow, how do I make sure that I'm not just like walking around the rim of the mesa the whole time, to abuse your desert metaphor?
Technology, like really. Okay, so first question is actually a little bit more difficult to answer. Um, so I'll be completely honest with you. I mean, you don't know, even if you run the code twice, if you get exactly the same energy function, right? This is one of the challenges we have in deep learning. I mean, you run the code twice, forget for a second this thing. I mean, you have a network. You're learning the simplest network to do, I don't know, MNIST, to classification. When you're doing the network twice, are you getting the same function? Because many functions can lead to the classification of MNIST. You run the network twice for different initialization, you may get something different, right? So there is a question. I mean, we know in this case the minimum is going to be in the same place. Otherwise, you could not be getting the same results. Is the landscape going to be always the same? The answer, I don't know. That's a complete honest answer, even though I want to say we always converge as we, it's like that would be nice to say, but I don't think I can say it directly. Second thing is actually easier because we're actually using, again, two steps. This is, again, very simple. You just think about methods that you know, like conjugate gradient. As long as you have the steepest descent direction, you're not going to move all around because you're going to improve based on your task, right? The only time you can move without, of course, steepest descent is when you're flat, when you're not moving anywhere. But as long as you're combining both the steepest descent and the tangential direction, you're fine. Just like you'll do in any other optimization algorithm that is multi-step, where you have more than one step. BFGS, conjugate gradient. If you look at Newton with thrust region, all of them are about the same ideas.
Thank you. What's your take on using optimizers like Shampoo, Muon, all those famous, pretty popular in the LLM world for GNN? Does it make sense? Or because usually those models are over-parameterized, like severely over-parameterized, and GNNs aren't that much over-parameterized.
So again, I didn't compare to every other optimizer out there. I can tell you that simple optimizers, that again, not the trained one, not the learned one, the simple ones, you can do better. But again, it's not surprising because you're learning them as a task. If you're going about what you call zero shot, and you have nothing, you don't know anything about the energy, then of course that you may be doing better by actually using something like conjugate gradient. Okay? But as long as you're training for the energy, why not train on more than one direction? Okay? That's basically what the message here.
Right. Thank you.
Any more questions from the audience? And if not, we can move on to the next presentation. So with Tal River. next, let's welcome Tal Amir to give his presentation on short-range oversquashing. Let's welcome him with applause.
Okay, thank you. So hello, everyone. I'll be speaking about our work titled Short Range Oversquashing. And this is joint work with our research group members, Yakov Mishayev, who is here with us today, and Jonathan Sverdlov and Nadav Dim. So, as we all know, many of the popular models for graph learning fall into the category of message passing neural networks, or MPNNs. However, while MPNNs are computationally efficient, they're usually successful only with a small number of message passing iterations, and typically no more than 4. And the closely related concept is the problem radius, which is the largest distance that information needs to travel on the graph in order to solve the problem. And naturally, using an MPNN dictates that the number of iterations need to be at least as large as the problem radius. So here in this example from the famous paper by Alon and Yahav from 2021, they showed the results of running several standard MPNNs with R+1 iterations on a problem of radius R. And as you can see already at R equals 5, the performance starts to significantly degrade. So this degradation was explained by two main explanations in the literature. One is the phenomenon of oversmoothing, whereby with the message passing iterations, the node features become increasingly similar to one another until they eventually become numerically indistinguishable. And the second one is oversquashing, which is the excessive compression of information into node features. Now, the term oversquashing ties several factors together. In the original paper, the authors say that large problem radius necessitates running a large number of message passing iterations, which leads to an exponential growth in the R-hop receptive fields of nodes, which in turn leads to information bottlenecks. And our goal here is to decouple two factors. The first is the large problem radius, which is known to lead to vanishing gradients. And the second is the phenomenon of bottlenecks, which is the actual compression of information in node features. Now, to distinguish between the phenomenon of bottlenecks and the vanishing gradients, we study a family of graph transfer problems. And the first problem we wish to consider is called the tree neighbors match problem, introduced by Alon and Yahav. So here we have a tree of depth R, where the leaves are sources, and there is one target node connected to the root. Now, each source node has a unique identifier, which is represented by its color, and in addition, it has a random label, a random discrete label, and the target node also has an identifier that matches one of the sources, and the nodes in gray are called central nodes, and they have a dummy identifier, and their sole purpose here is to conduct information. And the goal is to propagate the label from the correct source all the way to the target. Now, as you can see, information has to flow here from the leaves up to the root, and the number of leaves grows exponentially with the problem radius. So nodes close to the root become information bottlenecks in the sense that they must compress an exponential amount of information into their fixed dimensional feature vectors. And as we will see, this bottleneck effect, in fact, does not require exponential growth with the problem radius, and we can actually have bottlenecks even with the fixed problem radius. Now, the second problem we consider is called the ring transfer problem. And here we have one source connected to one target through two disjoint paths. And also here, the authors observe that performance degrades as R increases, and they explain this by vanishing gradients. And we confirmed this experimentally by evaluating the gradient norm of GCN trained on this problem. And indeed, we have exponential decay of the gradient norm, which indicates that we have vanishing gradients here. So far we've seen two explanations for oversquashing. The first is in the tree neighbors match problem, where rapid growth of receptive fields leads to information bottlenecks. And the second one in the ring transfer problem, where a large problem radius leads to vanishing gradients. And we will now show that these are two distinct phenomena. So for this, we have our first theorem, which says that the ring transfer problem can be solved by an MPNN with a constant feature dimension that is independent of the problem radius. And this tells us that the problem does not suffer from the bottleneck effect. So now we know that we can have vanishing gradients without having bottlenecks, and we also wish to show that the converse is true, namely that we can have bottlenecks without having the vanishing gradients. So for this, we introduce the following problem, which we call the two radius problem. So here we have n sources connected to n targets through one central node. And as you may expect, the central node becomes a bottleneck. And later we will see that solving this problem with an MPNN provably requires a feature dimension in the order of n log n. And thus this problem also theoretically suffers from the bottleneck effect. And we also measured this empirically. Here we evaluated several prevalent neural architectures on this problem. So in the MPNN category, we have GCN, GENE, GUT, and GraphSage. And we also tested the non-MPNN architectures. The first is a transformer, graph transformer, and the second one is an MLP, like a plain MLP applied to all the node features concatenated in arbitrary order. So as you can see, the performance of MPNNs degrades as you increase the number of nodes, and this is not resolved by increasing the feature dimension. Whereas transformers performs pretty well, regardless of the number of node features. One exception in the MPNN category is GUT, which somehow manages to postpone the problem, and but you can see that the accuracy of GUT exhibits a very high variability, as you can see in the very wide error bars in the plots. And it also took significantly much longer to train. But still you can see that an attention mechanism at least partially helps to resolve this problem. So now we ask, what if this is not the bottleneck effect? What is the culprit here is actually vanishing gradients or even oversmoothing? So we measured this empirically by evaluating the gradient norms and another energy called the relative MAD, mean average distance, which measures oversmoothing. It goes down to zero if and only if oversmoothing takes place. And as you can see, both of these energies maintain their order of magnitude along different values of n, which means that this problem does not suffer from vanishing gradients, nor does it suffer from oversmoothing. So now we see that we can have bottlenecks without having vanishing gradients. And this brings up an interesting question. Can the bottleneck in this specific problem be resolved by adding more central nodes? So here, instead of one central node, we have k central nodes. And we evaluated GCN on this problem. And we can see that not only did it not improve, but it actually impaired performance, which was bad to begin with. So in this problem, adding central nodes does not help. And the reason for this is that without an attention mechanism, each central node aggregates exactly the same information as the others. So adding more of them does not help. And neither will adding virtual nodes, because in this example, virtual nodes behave exactly the same as central nodes. And we also proved this theoretically by showing that solving this problem with an MPNN requires at least a feature dimension in the order of n log n, assuming that you use finite precision floating point arithmetic. Now, why is this a problem? First, since the required dimension depends on n, it is provably impossible to generalize on much larger graphs. And second, since this bound does not depend on k, you cannot improve it by adding more central nodes. And also, I want to add that empirically, even with the required embedding dimension, feature dimension and beyond, for large values of n, MPNN still fail. And we speculate that the reason for this is that in the aggregation step, the aggregation function needs to embed large multisets of feature vectors into a dimensional space, and it is difficult to do so without incurring distortion. And there also have been theoretical works on this topic of embedding multisets with low distortion. Lastly, there have been several explanations for oversquashing proposed in the literature, and all of them fail to predict oversquashing in our example. So let me go over them quickly. First, we've seen that larger problem radius is not to blame here because here the radius is fixed, it equals 2. And nor does vanishing gradients take place here. Another explanation proposed was poor graph connectivity, which was measured by spectral criteria such as the Cheeger constant or the spectral gap. And here we proved that the Cheeger constant is lower bounded by 1, and it actually increases with k because adding central nodes improves the graph connectivity. So spectral criteria or poor connectivity are not to blame here. Another explanation is based on the concept of Ricci curvature inspired by differential geometry. So here the authors defined curvature for edges, and they proved that edges with negative Ricci curvature make for information bottlenecks. However, here all our edges have 0 curvature, so their result is not applicable to our case. And lastly, another work pointed the factor of high effective resistance, which is similar to electrical resistance in electrical circuits. However, here the effective resistance in our graph equals 2 over k, which is upper bounded, it is independent of n, and you can actually make it go down to 0 by increasing k. So effective resistance is also not to blame in our example. And the conclusion is that existing criteria, while maybe sufficient for oversquashing, they are not necessary. So let me conclude. We've shown that first, bottlenecks and vanishing gradients are 2 distinct phenomena, and bottlenecks can occur even in small radius problems. MPNNs cannot handle bottlenecks well, not even if you add virtual nodes, whereas transformers can handle bottlenecks easily. So for more information, take a look at our paper, and thank you very much.
Any questions from the audience?
Hello, thank you very much for the presentation. 2 quick questions about the virtual nodes. The first one, you say somehow that all these central nodes that you designed will converge into the same vector. It doesn't mean that it's bad. Actually, the original paper that only graph classification showed that that information is all what you need actually to have a nice downstream performance. My second question is, you designed the central nodes, or what you call the virtual nodes, as similar. They are all connected to the same. But actually, if you connect them to different parts of the graph, then this problem of having the same vector is not present, right? Thank you.
Okay, so to answer the first question, actually the central nodes don't converge to the same feature. That's over smoothing. That's something else. Here, due to symmetry, if you don't give the central nodes unique identities, and their aggregation function is the same, they actually aggregate exactly the same information by their definition. So you may think that adding some more central nodes will somehow divide the load between the nodes, but since they all aggregate the same information, it does not practically improve the information flow on the graph, unlike electrical circuits. Sorry, what was the second question again?
Which was about how you define the virtual nodes. In your case, you connect them to all the nodes.
Yes,
That's why they
exactly.
aggregate
Yeah.
the same information.
Yeah, you just add nodes that are connected to all the rest of the nodes. So here they would act the same way, exactly the same way as central nodes. So we do not expect them to improve.
No, but imagine you don't connect them to all the nodes, but you connect them to some specific parts of the graphs.
Okay, so yeah, another way to try to ameliorate this would be to try to give unique identities to the central nodes or to introduce different connections between the central nodes. That's one possible way to try to ameliorate this. We tried playing with this concept, but at least from preliminary experiments that we conducted with unique identities, we did not see great improvement, but maybe with an attention mechanism plus what you said, it could, or with unique identities, it could improve results.
Thank you.
But anyway, an attention mechanism, and that's the bottom line, an attention mechanism can significantly improve information flow, and I believe it can also lead to better generalization to larger graphs. And you can also see from the practical results here that, yeah, let me go back a little bit. Yeah, so you can see the graph transformer is not bothered by the number of nodes. It handles well.
Any more questions?
I was curious about how and I think this might have been a reference to the previous paper, how the radius is like, how you had like different graphs with different problem radiuses. I think that's what you called it, like how those are constructed.
So that problem was presented in their original paper. It's called the neighbors match problem. It's like, yeah, basically information needs to flow between distant components in the graph. I can send it to you later if you want.
Okay. Yeah, thanks.
More questions?
Yeah, thanks for the nice talk. So my question is more about the terminology. So, like whether it makes sense to name something shorthand over squashing, because at least my understanding is over squashing was defined in terms of the distance. So, like whether just we should rename, or you should maybe come up with a different name for the case where you just need a larger embedding to encode the neighborhood of a
Yeah, so I agree that there has been a lot of confusion in the community with the naming of the different phenomena because several distinct phenomena were bound here together under the umbrella term of oversquashing. And that's what we're trying to do here, to distinct between the different phenomena under the umbrella of oversquashing. As one of the conference participants told me yesterday, I don't believe in oversquashing. So oversquashing is real, but it stems from several different factors. And I definitely agree that we need better naming.
Just a follow-up. Is there like any other case of bottleneck that you wouldn't call short range over squashing, that you call something else? Are these two things like the same, or is like bottlenecks like a larger class of issues that include other sub-problems?
So my personal opinion is that the term oversquashing should be reserved for bottlenecks because you literally need to squash information into fixed dimensional feature vectors.
Yeah, thank you. Thank you.
So do you think whether sampling methods can somehow mitigate the oversquashing? Because, for example, if you use GraphSense, so you first sample a subgraph, and then in this subgraph, the neighborhood number will be much smaller, so the information will also be less for each subgraph. Would that be better?
I believe that in this case, no, because you actually might miss out on the correct source node if you sample a subgraph that does not include it. So no.
Okay, thank you.
I mean, it would not improve the connectivity of the graph if you take a subsample of it, right?
Yeah, thank you. I don't fully understand it, but yeah.
Yeah, okay, so let's discuss it later.
Any more questions from the audience? And if not, let's thank Tal for giving this excellent presentation.
Thank you.
next, let's welcome Gail Michnick from UCSD to give us a talk on learning Kronecker structured graphs from smooth signals.
Hi everyone, this is joint work with my previous PhD student, Changhao Shi, now an engineer at Google. And what Changhao was doing through his PhD was learning graphs from complex signals. In this case, we're learning the Kronecker graph from signals with a smoothness assumption. So I'll start with a bit of background. This work doesn't have any graph neural networks in it. We're a bit unique, I think, in the conference in that sense. So this is coming from the field of graph signal processing. I'll give a tiny bit of background, and then I'll go into our approaches. So graph signal processing tries to generalize classical signal processing from regular grids, time series, images to irregular domains that we are all interested, graphs and networks. In different applications, primarily one I'm interested in is brain connectivity, but it's also been applied to shape analysis, traffic networks, social networks, and so on. So we can leverage classical signal processing tools now on irregular domains. But a problem that we have is that many times the graph isn't actually available. So I work a lot with neuroscientists, and we're interested in measuring something called functional connectivity. We want to learn what is the connectivity that the activity of the neuronal network or the brain regions implies. So we have anatomical connectivity, and we don't know if that maps onto the co-activation of different brain regions. And one of the solutions is to learn the graph from the signal itself. So we can treat an fMRI time series. Every time point is a graph signal, and then we can learn the signal, then we can learn the graph so that the signals are smooth with respect to that graph. So that is the graph smoothness assumption in GSP. So given a matrix of signals, we could think of every column as being a signal on your graph, and every row is a signal on your node. And we're going to learn the graph Laplacian from this collection of signals, where two fields have tried to address this problem. So with GSP, we're treating this through the graph smoothness assumption, where we could have different regularizers in order to constrain the graph learning. And then in graphical models, this has also been addressed in covariance estimation, constraining the precision matrix to be a Laplacian, adding terms on the log determinant, so the Laplacian is connected, and then also constraining the sparsity of the network, because typically in real-world data, we have sparse graphs. So we're trying to get from a connection of signals to what is the underlying graph that generated them. The difference here from covariance estimation is because it's a graph Laplacian, our graph has necessarily non-negative weights. So there's been many work done on this in the single way case, when we're trying to learn a graph along only one mode of the data. But in many cases in the real world, our data is actually multi-way. So we could think of it as a coupling of different domains along different modes or axes of the data. And kind of the most classical multi-way data that we're all familiar with is images. So we generalize from a path graph representing time to two path graphs representing images. And then the Fourier transform becomes a multi-way Fourier transform, which is the 2D DFT. Moving into problems that we care about more, for example, in sensor networks, we have graph temporal structure. So we have a network of sensors. At each sensor, we are collecting observations over time. Again, from a Fourier perspective, we could then think of this as a coupling between the classical discrete Fourier transform and the graph Fourier transform. This is the time vertex framework. And then we can generalize this even more to having a graph underlying each of the modes of our data. So we can model, for example, social networks this way and other kinds of hierarchical structures. And then the graph Fourier transform generalizes to a two-dimensional graph Fourier transform, or even higher order if you have, for example, tensor data. So in certain cases, we have an integration between classical and graph domains, and in certain cases, we are just addressing the fully graph domain. And now, given a collection of factor graphs, the question is, what kind of structure, interacting structure, do you want to model between the different modes or axes of your data? So there are different ways to calculate what's called a product graph, which is the shared structure now between the two factor graphs, and these model different types of interactions. So a Cartesian, which is what, again, we're most familiar with, for example, from images, the factor graphs are separable in tensors. In the tensor product or the Kronecker product, just is what we're dealing with in the paper. In this conference, you could think of, if I'm considering the time vertex case, moving from one time point to the other, the information at the node at the current time step is influenced from the neighbors in the previous time step, as opposed to the Cartesian product, where the influence is only from a node to itself. And then the strong product is a sum of both of these. There are nice spectral properties to the adjacency matrix, given these different types of products, that then gives us properties of their eigenbasis in terms of the eigenvalues and eigenvectors, but this holds for the adjacency matrix and not the graph Laplacian. In the case of the Cartesian product, this does also hold for the graph Laplacian, but for the Kronecker product and the strong product, this only holds for the adjacency matrix. And I'll show you why this matters. So what is the challenge when we're learning product graphs? Consider two rather small graphs. I have 20 sensors. I have 36 time points. If I was to use smooth graph learning, not using the product structure at all, then I'm learning a graph with 20 times 36 nodes. And that means that I'm estimating around 500,000 connections, even for these two relatively small graphs. This is naively. But if we impose a structural prior that the large graph is a product of the two smaller factor graphs, then we only need to learn on the order of P1 squared plus P2 squared connections. So we've greatly reduced the number of parameters that we need to estimate in order to learn the overall graph. So we had earlier work on this for Cartesian product graphs and AI stats. Within GSP, we have an underlying assumption on what the signal distribution is, filtered by the unknown graphs. And then we formulated a penalized maximum likelihood estimation given a graph smoothness term, the log determinant barrier term, and then a sparsity term on the graphs. Where the nice thing for the Cartesian product graph, as I mentioned, is that the Laplacian is separable into the individual factor graphs, and the problem itself is convex in both variables that we're trying to find. Furthermore, when we do projected gradient descent, we have an expensive matrix inversion here that we can leverage properties of the spectral decomposition of the Laplacian in order to further reduce computational complexity. So we can use the eigenbasis of the Laplacians that we're trying to find in order to do this matrix inversion. The issue then, when we go into the Kronecker structured graph learning, so we're now trying to learn a Kronecker product graph from our data, is that the Laplacian isn't a Kronecker product of the factor graphs. So the problem is no longer separable as it was for Cartesian products. So our smoothness term cannot separate into two separate smoothness terms. We did devise then an alternating minimization algorithm. So we fix one factor graph and we learn the other, and then vice versa. We fix the second one and we learn the first using projected gradient descent, where we are imposing that the weights are non-negative again because we're learning a graph Laplacian. So we have non-negative weights. Another thing that we did as part of this work is that we observed that the strong graph product, we could actually write it out as a Kronecker product minus the identity matrix, where the Kronecker product, all this does now is that it adds self loops to your graph Laplacian. So we can take the strong graph product and plug it into our penalized MLE for Kronecker products, and then also solve within the same framework strong graph product learning. In terms of theoretical results, so this builds on prior results from graphical models. We have a few reasonable assumptions on the sparsity of the factor graphs and bounding their degrees and their eigenvalues. We can show existence of the maximum likelihood estimator and uniqueness of each of the maximum likelihood subproblems. So the overall penalized maximum likelihood is biconvex with respect to each of the factor graphs. So if we hold one fixed, the problem is convex in the other that we're trying to solve for. And then finally, we have a consistency result. So given the assumptions that we have given a sufficient number of signals, then the minimizer that we find, the product Laplacian, is asymptotically consistent with respect to the true Laplacian with high probability. So and we've improved on a previous result by a factor of square root P1, P2 over the sum of the sizes of the individual factor graphs. So in this case, we need fewer samples in order to find the true graph theoretically with respect to prior work in this field. So we had a few synthetic simulations where we actually know what the ground truth structure is. We took a variety of random graphs and then did either their Cartesian product or their Kronecker product and tested with comparison to alternative product graph learning and product graphical models. And we can show that we have the best performance, both in terms of the relative Frobenius error of recovering the graphs for both the Cartesian product case and also for the strong product case across a variety of different graph types. And then also in terms of recovering the edges themselves. For real data, again, I collaborate with neuroscientists. We have a data set here that looks at epilepsy with EEG signals. And for one of these patients, the seizure, the epileptic seizure, isn't observed in the EEG in terms of the magnitude that's recorded with the EEG. However, if we apply our product graph learning, then we can find the presence of the seizure in the graph itself. So we can see that during the seizure, we have a more densely connected structure here that actually corresponds to where the patient has a brain lesion. And furthermore, in time, we can see that during normal time points, we recover the classical path graph that we would expect for time series, but during seizure, we have a much broader span over time. So the effect of time of history is much more dominant. Furthermore, we looked at other patients whose seizures are observable, and what we found in these patients, calculating, again, the graphs using our Kronecker graph learning, is that if we look at the degree distribution during normal time points and during the epileptic seizure, there's a significant difference in terms of their degree distribution. So we can identify, again, the seizures just from the graphs themselves. So to summarize, we have a principled toolbox over the span of 2 papers that addresses recovery of multi-way network structure. Our previous work on multi-way graph learning leverages spectral properties of the Cartesian product graph in order to find Cartesian products from data. And then in this work, the Kronecker structured graph learning, we address the non-convex penalized MLE with an efficient alternating optimization scheme. We update each factor graph in turn, and we show strong theoretical guarantees for faster correct convergence. So if you'd like to see either of the papers, I have the QR code. I'd like to thank Cheng Hao, who really led this work, then various funders, all of you for being here today. Thank you.
Given the limited time we have here, so we will take only one question. Any questions from the audience? I don't see any online questions either, so let's thank Gail for giving this excellent presentation. And that concludes today's oral part.
So let's welcome our second keynote speaker, Professor Hagai Maron, who is Assistant Professor and Fellow at the Faculty of Electrical and Computer Engineering at Technion and Senior Research Scientist at NVIDIA Research in Tel Aviv. His primary research interest is in machine learning with a focus on deep learning unstructured data. Thank you so much.
Hi, everyone. Thanks for organizing this. I'm a big fan of LOG. I think that we need it as a community, so I'm really happy to talk here. I'm going to talk about a recent line of work that we are pursuing in our lab. So maybe the first thing would be to kind of say what we're interested in. So I tried to think about it when I prepared the slides, and essentially what my lab is interested in is, given a data type, how can we process it with a neural network? What is a good way to do that? And essentially, this is like the underlying question behind graph neural networks, right? Or the graph learning community. How can we consume graphs? And we are kind of trying to generalize that. So we do have a specific way of doing this. This is not the only way, but we do it quite a lot. And the idea is to first analyze the symmetries of the data, and then to design symmetry-aware architectures, and use them for the data type. And in general, we're interested in all kinds of symmetries. We will speak about symmetries in a few minutes, and I will explain exactly what I mean by symmetries. But we do have a focus on permutation symmetries and on GNNs. So we worked quite a lot on graph neural networks and related problems. And in the last 2 years, my lab is working on a new interesting data type that we call neural artifacts. And this is what I'm going to talk about today. So the TLDR of this talk is as follows. So we think about weights, gradients, internal representations of deep models as a new family of data types. We call them neural artifacts. Those artifacts have very interesting structure, a lot of graph structure inside, and a lot of interesting symmetries. In our work, what we essentially try to do is to design symmetry-aware architectures for those data types. And we believe that there is a huge potential to be, for this direction to be impactful going forward. So to enable a lot of things, tasks on weight spaces, on gradients, and so on that are currently limited due to all sorts of things. Okay, so the outline of the talk is as follows. We will first try to explain what are neural artifacts and what are their symmetries. Then we will have a very quick tutorial on learning with symmetries. And then we will see many examples. We will see examples on weights, we will see examples on internal representations, and on gradients. Okay, so what are neural artifacts? We will start from maybe the most common artifact, or maybe the most basic one, which is weights. So if you look online on Hugging Face, for example, you can see huge repositories of neural networks online, trained neural networks that you can just download. And the idea is that we can think about those as a new type of data, right? We have a collection of structured data types, and we would like to maybe analyze them or to understand what's going on, the structure, perhaps to generate them, and so on. So we want to think about weight spaces as something very similar to images or text, right? For images and text, we know that we can analyze them using neural networks. We can generate them, and it's becoming very, very nice these days, generation. Can we do the same for weight spaces? And alongside with weight spaces, two other important data types kind of emerged. Those are internal representations, which are the activations, the logics, the attention maps that are generated during the neural computation. And the second data type is gradients, which are formed during the training process. And the main question that we are trying to ask is, can we do anything interesting with neural artifacts? So let's try to see what can we do if we have successful methods for learning on neural artifacts. So maybe the first example is the following. I have some neural network, and I would like to predict the accuracy of this neural network on some data set. So one way to do it would be to just evaluate it on the data set, right? Louder. Okay. So we would like to evaluate it, but that takes a lot of time if the data set is large. What if we can train a neural network that will take the other neural network as input and will just tell us the accuracy on the data set? That could be cool, right? Another interesting application would be to edit neural networks. So let's say that I have a neural network trained on some domain, and then I want to edit it. So editing could be a lot of things. Think about adapting it to a new domain, or binarizing the neural network, or a lot of things that we usually do to neural networks. So one way to do it would be to apply some training in order to adapt the neural network to the new domain or something like that. But what if we could use a neural network that takes the neural network as input and outputs the edited neural network? That would be nice, right? Another example is on implicit neural representations, or INRs in short. So INRs is a certain way of modeling data as neural networks. So what we see here in this example is a way to represent an MNIST image using a neural network that takes two inputs, X and Y, and outputs the intensity level. So if we want to essentially model all the MNIST data set using INRs, we will have to repeat this process for any image in the MNIST data set. And then we can try to do the following thing. Can we classify the class of the image only by looking in the neural network representation? So for images, it doesn't make a lot of sense, right? Because we kind of know how to work on images, but INRs are pretty interesting creatures, and you can actually represent whole scenes with INRs. Those are called nerves, for example. So for nerves, we don't really have a good way to apply deep learning to them. And essentially, nerves are just neural networks, right? They're just a data set of different nerves is a data set of neural networks that you want to process. What can we do with internal model representations? So first of all, one thing we can do is to analyze, for example, how LLMs generate text. So here we see a sequence of tokens being pushed into this LLM. And think about this activation tensor that we can extract from the computation process. It has layers times tokens times features. And what if we could train a neural network to tell us whether the LLM hallucinated during this computation? That would be useful, right? Another thing we could do with it is to edit the activations in order to steer the generation away from hallucinations, for example. Lastly, for gradients, we can also do a lot of interesting things. So first of all, we could try to learn adapted gradients. So for example, if we get a bunch of gradients at a certain position, we might be able to merge them together into a better gradient that goes in a better direction, for example. Another thing we could try to do is to compute a specific weight delta in order to achieve some goal, for example, to edit the network. And we can actually query curvature information. We will talk about it, I think, in 20 minutes or so. So hopefully, you now kind of believe that if we had the machinery to apply neural networks to neural artifacts, that would be useful. And the question now becomes, how can we apply deep learning to those artifacts, right? And the key observation is that neural artifacts have a rich symmetry structure, and we must account for this in order to learn over them. So let's do a quick survey of symmetries. I'm not going to go over all the symmetries, but we're going to talk only about MLPs here. So let's start with weight spaces. An MLP essentially consists of three matrices, weight matrices, perhaps with biases, but let's say that we don't have biases here. And one very nice property is that we can permute the internal neurons. Okay, so you can see in orange and in green here that we can permute those neurons. And we essentially get different weight matrices, but they compute exactly the same function. So the way to see it is just to multiply and to see that the permutations cancel each other. Okay? So we essentially want to treat all those neural networks that compute the same function as the same thing. And this is a symmetry of MLP weight spaces. This is one kind of symmetry. There are more. But let's see how this thing transfers to activation spaces. So when we talk about activation spaces, we talk about all the concatenations of the internal representations. In MLP, it would be H1 concatenated with H2 here. And one thing to notice is that if we apply permutation to H1 and another permutation to H2, for example, we get the same computation process, just, with a different order of the neurons. So we would like to treat those as equivalent as well. And finally, for gradients of MLPs, in general, gradients, they live in the weight space itself, right? They have the size of the weight matrices. But there is a very nice property that allows us to decompose gradients of single points. And then what we get is signals that essentially live in activation spaces, not in weight spaces. So also for gradients, we get very nice symmetries of applying permutations to those signals that come from the gradient decomposition. So in all these cases, we have a symmetry group that permutes the entries of the neural artifacts. Here, specifically for this three-layer neural network, we have G equals SD1 times SD2. D1 and D2 are the dimensions, internal dimensions of the MLP, and Sn is the symmetric group on n elements. So each artifact type essentially lives in a different vector space, which is essentially a group of representation, and we have a different action on it. But the same group acts on all those artifacts. And again, the main message here is that if we want to process those artifacts, we want artifacts that belong to the same orbit to be considered the same. And this should be kind of clear to this community, right? If we process graphs, one of the main things that we would like to ensure is that the order of the nodes is not something that the model would use, right? We would like to be invariant to the order of the nodes. So you can think about it as a generalization of the same concept. Okay, so we talked about MLPs, and we talked about permutation symmetries, but that's not all. So permutation symmetries are kind of fundamental in weight spaces and neural artifacts, but there are many more symmetries. So just as an example, think about attention maps, for example. An attention map is an n by n matrix. And for us graph people, we can easily think about it as a graph, right? So we can think about graph symmetries in attention maps. For low-rank adaptations, those low-rank weight deltas that we add to very large models, we have very special GLD, general linear group symmetries, because multiplication of A and B could be changed to AZ and Z minus 1B, right? We can essentially put any invertible matrix inside, and then we get different parameterization to the same weight delta. And the list goes on and on. In transformers, we have attention head permutation symmetries. We also have similar GLD symmetries for the attention computation, and so on. So the main thing I would like to kind of stress here is that this is a whole zoo of symmetries. And if you like this kind of geometric deep learning perspective on things, this is heaven, essentially. A lot of things to do, very interesting stuff. Okay, so we're done with talking about neural artifacts, and I would like to briefly talk about learning with symmetries. So what are symmetries? Basically, they are transformations that keep the properties of the object unchanged. And a good example to have in mind is images with translations, right? If I apply a translation to this cat, this is still a cat, right? The image is still the same image. And the main thing is that learning tasks are, in most cases, invariant to those kind of transformations, meaning that we don't really care about those transformations. We care about the object itself up to this transformation. And maybe the whole idea behind geometric deep learning is to constrain our models to architectures that are invariant to those kind of symmetry transformations. Okay? So why does that make sense? I hope that it makes sense for you in general, but let's try to talk a bit more about it. So the thing is that invariant model essentially treats all the symmetric copies or the orbit under the group action of the input in the same way. So this dramatically reduces the need for training data, right? So this is very similar to what we know from graphs. If you try to train an MLP on adjacency matrices, you know that it doesn't work. You need certain structure in your architecture in order to make it work, and the structure is invariance to permutations. So for large groups like neuron permutations that we deal with in neural artifacts, the number of equivalent copies, like in graphs, is exponential. And that really makes learning on neural artifacts impossible if you're not invariant. So what is invariance formally? We have a group G that acts on Rn, and a function is called invariant if applying the transformation in the input does not change the output. A generalization of this concept is equivariance. In that case, applying to the input commutes with applying to the function. So essentially f of tau equals tau of f for any tau in the group. A good example for that is edge detection, but for graphs, we can think about node classification, for example. This is an equivariant task, right? So if we change the order of the nodes, we would like the output nodes to be permuted as well. So how do we design invariant and equivariant neural networks? There are many ways, but one very popular approach is to compose simple equivariant layers. And this kind of very simply follows the idea of CNNs. So you kind of come up with a good primitive, basic layer that you would like to use, and then you can concatenate it or compose it several times with pointwise nonlinearities. And if you want an invariant function, you can apply summation or any type of readout function. We have readouts in graphs, but we also have similar ideas for general symmetries. So the simplest and most common choice for those simple layers is linear equivariant layers. In the case of permutation symmetries, these come from parameter sharing. So we can see here examples for translations, where the group is Cn, the cyclic group of n elements. We can see set symmetries, like in deep sets, and we can see the case of no symmetries at all. There are different examples. For example, message passing neural networks, those layers are not linear, but they are a good choice for a primitive to use in order to build the networks. And people have also used polynomial layers, which is very interesting, but we will not talk about it more here. Okay. One last bit that I would like to talk about in this very fast course on learning with symmetries is the expressive power. So what does expressive power mean? It means given a family of models or architectures, what is the space of invariant and equivariant functions that we can approximate with this family of models? And ideally, we would like to be able to approximate all functions that are invariant to the symmetry that we have. But in many cases, in real life, and in graphs, this is a very good example, we don't have this, right? So message passing neural networks, we know that they cannot really approximate any function, any invariant function on graphs. For example, counting the number of triangles in the graph, right? This is a well-known. But this thing comes up in many other domains as well. So after we design our model class, we need to think about what we get from the expressive power point of view. Okay, so let's do a short recap. We talked about neural artifacts. Those are weights, internal representations, and gradients. And those are emerging data types with very interesting applications. Neural artifacts are complex. They have symmetries. And in order to learn over them, we need symmetry-aware architectures. And what we will see now is a series of concrete examples. Okay, so let's start from learning on weight space. And we will focus on MLPs here. So an MLP is just a composition of linear affine layers and pointwise nonlinearities. And when we think about processing an MLP, what we really think about is to concatenate all the weights and biases into like a very large vector and to apply some function to it that will output different weights and biases. Okay, this is the general case. And about 5 years ago, a bunch of people came up with the idea to learn on those parameter spaces and essentially made the first leap of faith in this direction. And what they did is kind of simple when we look at it now. They took all this concatenation of weights and biases and applied some off-the-shelf architecture over it. The interesting thing is that they were able to make it work for several tasks, which was, kind of, I would say, surprising at that time. So let's take a closer look on this kind of naive approach. Now we can call it naive, but back in the day, that was like really interesting thing to try. So they vectorize all the weight matrices, and then let's say that we apply a fully connected network to this concatenation, right? This would be like the first thing to try. What are the problems with this approach? Two main problems. First, you will get a huge parameter space for the neural network that consumes your weights and biases, right? So think about the neural network that, like the input neural network that would have like 100K parameters. This is a very small one these days. But a fully connected layer on those will have 10 billion parameters already, okay? Second thing is that this architecture ignores the symmetries. So kind of in a more simple terms, the networks must memorize equivalent models. They cannot generalize between the same classes of models that are connected by a group element. Okay, so like 2 years ago, we started to think about this problem and try to understand how can we come up with an equivariant architecture for weight spaces. And the main observation that we had is that essentially weight spaces is a concatenation of all the weights and biases. And the symmetry group acts in a very interesting way on those. It acts on the W's and on the biases independently, right? You cannot move between one W to other W. You just permute it within the weight matrix or within the bias vector. In more mathematical terms, this is called the direct sum of representations. And by using this idea, we can use a very simple result that shows that essentially equivariant maps of direct sums of representations decompose into block structure. That means that if we map from one direct sum to another one, we will have blocks corresponding to the input and output vector spaces in the direct sum. So in our case, we actually use this a couple of times. First, we use it to decompose the weight space and the bias space. And then we get a block matrix that looks like that. And then we use it again in order to decompose each one of those blocks into smaller blocks that map between specific weight and biases, like Wi to Bj, or so on. What we show is that those layers follow a very natural block structure, as I just said, and those blocks can be implemented by 3 basic operations. So they are extremely simple. You can use broadcasting, pooling, and fully connected operations. This could remind you a bit of graph neural networks, right? Graph neural networks, we also use fully connected layers, pooling mechanisms, broadcasting sometimes. And there is a connection here. We call those architectures deep weight space networks, or DWS nets in short. From the expressive power point of view, we were able to show that we can approximate the evaluation function. What does that mean? It means that given a specific set of neural networks, input neural networks, we can find a DWS net that evaluates them on any point, essentially, that we want. And this, like, more generally means that those DWS nets, they can think about or treat the inputs as functions and not only as lists of weights and biases. And one thing in particular this thing implies is that DWS nets can separate MLPs that represent different functions, right? Because we can just evaluate them in this particular point in which they fare. And this opens the way to use stronger expressivity results like the Stone-Weierstrass theorem and similar things. Okay, so let's see some experiments. What we have here is an INR classification experiment where we just want to predict the class only by looking at the weights that for each INR that represent the image. So let's start. If we just apply an MLP, not taking into account the symmetries at all, we get 17% on MNIST. That's very close to being random, right? One thing we could do to eliminate symmetries is to perform an alignment procedure. So this is similar to the graph isomorphism problem in graphs. We can try to find permutations that best align neural networks. This is also this is NP-hard in general, but you can use methods that try to approximate that. It takes a lot of time, of course. But even if we do this pre-processing step that takes a lot of time, we only get 60%. So this is a nice, jump from the standard MLP just applied to the weight spaces, but still not good enough. So what we learned from this is that symmetries matter, but there is probably something better that we can do other than alignment. And what we see is that DWS nets, they get 85% here, and more modern networks approach like 98, I think, or 99, so practically close the gap from MNIST on images as we know them. And this doesn't necessitate any type of pre-processing, nothing like that. You just use a neural network that respects the symmetries of your data. Okay, so in many cases, we see papers in which you get like 2% improvement, and this is a lot, right? When you try to work on data types with symmetries, you will see jumps with like 50% or so. This is that meaningful. Another experiment that I like to do is the following one. We try to kind of understand the sample complexity. So what do we have here? We have the y-axis gives us some measure of the loss and error, and the x-axis gives us the number of samples we used for training. So being down means that you need less training data in order to get smaller error, right? And you can clearly see that DWS nets, the symmetry-aware architecture, are much better. By the way, the best thing after that is the MLP plus alignment, which again tells us the importance of symmetries, okay? And this is for a very simple data set that we created. It's not like something fancy. Okay, so we did this paper. It was ICML 2023. And in that time, several other groups were working on the same ideas. So in particular, I would like to talk about two groups. Ellen Zhu et al. from Stanford University came up with several very similar designs for neural network, for equivariant neural networks for weight spaces. And also Tran et al. From the University of Singapore came up with several very interesting ideas in the same direction. So if you're interested, look at these. I think those are great papers. Okay, and now we get to the limitations. So maybe it sounded like we solved the problem, but the answer is no, unfortunately. So DWS nets are designed to single input architectures. So you can think about an MLP with K equals 3 layers and D equals 128 neurons, for example. If you get a new MLP with 4 layers, you cannot really apply your DWS net to it. So it's like a GNN that is kind of can only work on one particular graph, which is limiting, right? Also, I didn't tell you about it, but coming up with those layers is kind of tedious, very long derivations. You can see the tables that we ended up having in the paper of all the different blocks that we need to have in order to map weights to biases and so on. So in general, this motivates a more flexible approach to weight-based learning. And this involves graphs. So essentially what happened is that I showed this paper to then student, Derek Lim, now at OpenAI. And I told him, well, this weight space direction is very interesting. And he said, yeah, but essentially neural networks are graphs, right? So why don't you just apply GNNs to those? And this was a very simple observation that later led to a paper that we did. So the idea is to take the neural network, to represent it as a graph, and then just apply a GNN. For MLPs, this is quite simple, right? We have a bunch of input nodes, a bunch of output nodes. We have connections between the nodes, which are the edges. And we have edge features, which are just the parameters, right? Okay, so that makes sense. And this actually gives us nice advantages over DWS nets. So the biggest advantage is that we can now process different architectures using the same neural network, right? So as long as you can represent your architecture as a graph, you can apply GNN to it. That's very nice. You do need to come up with primitives to kind of represent different neural operations like attention, normalization, all that stuff. And there are many questions of how to do this in the right way. But again, this is a significant leap forward, I think, in terms of processing diverse neural architectures. The second thing is that if we restrict ourselves to MLPs, we can show that we don't lose expressive power. So we can still kind of evaluate the inputs as functions and so on. And one other advantage is that we can actually use all the different very nice architectures that our community came up with for graphs now for weight spaces, right? So if you want something with attention, for example, you don't need to code it yourself. You just need to take a GNN that applies attention, and that's it. So this thing actually gives us like a democratization of weight space learning in terms of the using those GNNs. And of course, we were not the only ones to think about it. So Kofinas et al. From the University of Amsterdam at the same time came up with the same idea, very nice paper. And there was a follow-up paper by people from the University of Athens that also added scaling symmetries to those neural networks. Okay. So the last thing I would like to talk about in weight spaces is low-rank adaptations. So first of all, what are those low-rank adaptations? Those are weight matrices that we can add to very large models. Those weight matrices are factored. So they are essentially B times A, where B and A are low-rank matrices. And this allows us to fine-tune models, but use only very small number of parameters. It gives us faster training and so on. Those are extremely popular these days. You can actually find like repositories of LoRa's for specific models, as we see here on the right side. And download LoRa's that do all sorts of things. And our question here is, again, how can we process LoRa's? And according to what we discussed up to now, we know that we need to understand the symmetries. So LoRa's have an interesting symmetry structure. We can actually multiply by any invertible matrix and get a decomposition that is equivalent, right? So this is very different than the permutations that we mentioned before, but still valuable and interesting to learn, to study. So what we did in the paper that we are going to present here in this conference is the learning on LoRa's architectures, or LOL in short. We developed several architectures that respect these symmetries, and we showed that it works very well on several interesting tasks, like predicting the accuracy of the fine-tuned models or predicting the properties of the training data that was used to create the LoRa, and so on. Okay, so we move to the next step. Now we will talk a bit about learning on internal representations. And in this part, I will talk mainly on internal representations of LLMs. Okay, so again, we have a sequence of tokens being processed by an LLM. And this gives us a bunch of internal representations that could be very interesting to process. The first type is the output token probabilities, essentially a sequence of probability distributions that give us the next token, right? Second thing is this tensor of internal activations that we mentioned earlier. So this is a tensor, 3 tensor of tokens by layers by internal features. The last thing is attention maps. So we can think about attention maps as some kind of an adjacency or affinity matrix, right? They give us the connections between different tokens. And processing those internal representations could be very useful. In general, what we are thinking about now is to do text generation analysis, to try to explain or to detect certain things that happen while LLMs are generating text. But you can think about many other things that can be done with this kind of approaches. So essentially, in order to process this, you need to account for their symmetries. I will not go over the symmetries of all those data types, but I can talk about it later if you want. Today we will talk about attention maps and how to process them. So what are those attention maps? They are essentially an n by n by L tensor holding all the attention scores in all the blocks of the LLM, right? N is the number of tokens in this case. So as I said, this has an affinity matrix structure between the tokens. And this pretty much looks like a fully connected graph, right? With some edge features over it. So what we propose to do is to define a graph from this affinity tensor and then apply a GNN to this graph. And we were able to show that theoretically our approach can approximate several state-of-the-art approaches. So we can think about ourselves as a generalization of those approaches. And practically, our method works better consistently. So I think for our community, it's pretty interesting to see data that comes from, this is a very different type of data that we are used to work with, but still this is graph data, and GNNs are very effective here. So this could be very interesting for you folks to kind of maybe think about as a new emerging graph data type. Okay, so lastly, I want to talk about gradients. So we all know gradients are central in deep learning. They drive our optimization algorithms. They are used for model editing. They are used for model analysis. And our main idea here is to design neural networks that can take gradients as input and allow us to automate those things, right? So we have three main design considerations. I will go over them briefly. First is that processing sets, we would like to process sets of gradients rather than single gradients. And we will see in a minute why this matters. Second thing is that we would like to utilize the rank 1 decomposition of the gradients. And third thing is that we would like to account, of course, for the gradient space symmetries. So let's go over them one by one. So the first key principle is to process sets of gradients. And the idea here is that if you process sets of gradients, you're in a specific weight space point, and you process multiple gradients of different data points. Then this essentially gives you approximate information into the curvature of the loss landscape, which could be very interesting if you are trying to make optimization better, for example, right? So we would like to process sets of gradients. Second thing is that we would like to utilize the rank 1 decomposition. Okay, so this is how a set of standard gradients look like for an MLP. And this is how it looks like when we use this decomposition. Okay, so this dramatically reduces the size of the input, which means that we can operate on larger models. And the nice thing about it is that actually this decomposes the symmetries as well, as we mentioned briefly before. So instead of those symmetries that we saw for weight spaces, we get set symmetries for activation spaces, which are easier to deal with. So we came up with an architecture that does all those things together. Essentially, it is you can think about it as a generalization of deep sets to those type of data. We were able to show some approximation results and also to show that processing sets of gradients is more expressive than processing like the average gradient, which is something that many methods do. And the main application that we had in mind in this paper is learned optimization. So the idea is that you can calculate the gradients, and then instead of averaging them and applying them in the optimization process, you can apply another neural network, our RAD MetaNet, and kind of learn a better direction. So think about this tool as something that allows you to look into the curvature information. And what we see here below, this is a real example, right? It's not an illustration of an optimization that we did with our approach. So you can see that we have a very anisotropic pattern here, loss landscape. And you can see that SGD goes into these well-known zigzag patterns that we know it has. The other learned optimizer, which is a simpler one in green, does better, but still kind of has this problem. And our learned optimizer kind of mitigate this problem. We actually did it for real data sets and real architectures. So what we had here is like a very simple two-parameter architecture for visualization. Here we have MLPs and transformers, and we can see that it improved the optimization process significantly. You converge faster, and so on. Okay, so I would like to conclude now. Neural artifacts are becoming very exciting data modality, I think. And I think that graphs play a key role in representing neural artifacts. So we saw two examples today, right? We saw representing neural networks and weight spaces using graphs, and we saw using attention maps and thinking about them as graphs. Another key thing here is that equivariance is extremely important. We cannot really do anything without taking care of equivariance. There are many, many exciting directions going forward here, both on theory and on applications. And we actually had our first workshop. It was in Singapore, 2025, this year, on weight spaces as a new data modality. I think it was a huge success. It was very interesting. A lot of people came from many different communities. And I think that the graph community should definitely be a part of our weight space community. Yeah, that's it. This is a list of all my collaborators, which were extremely helpful and led parts of those projects. And specifically, I would like to point out Fabrizio and Guy. Fabrizio is my postdoc, now looking for a position as a faculty member. And Guy is my PhD student, and he's looking for a postdoc position. Both are amazing. So if you are looking for something like that, talk to me or talk to them. I will be happy to kind of connect. And yeah, this is the list of papers that I mentioned today. And I'm very happy to answer questions and also to talk about it more during the poster session or in the breaks.
Yeah, thank you so much for the great talk. We have one question from the online forum. So I think they were referring to the block decomposition that you talked about. And they ask, can this group operations be extended to layer swapping, and how this fits with operations that cannot be decomposed in like basically nonlinear.
I see. Layer swapping is interesting. I think maybe we can do something like that. So maybe the simpler thing that we can do, think about skip connections, for example. So if you have skip connections, you can account for them in the symmetry because they essentially couple symmetries together in our network. So we don't have different SDs for those spaces. But I think it's interesting to think about it more. I'm not sure that I have something too smart to say about it now. The other question was, what can we do with the block decomposition, right?
With nonlinear narrative.
So essentially, for any type of data, you have different symmetries. You need to understand the symmetries and to come up with good, techniques in order to come up with the layers that respect those symmetries. So it depends on the data type, but this is just our work as researchers. And if you have interesting symmetries, we have interesting work. So I think about it as a good thing.
Yeah, thank you for the answers.
My question is, how does this approach compare with probing?
Oh, interesting. So probing is essentially another way you can think about processing weight spaces. By the way, probing is essentially learning in activation spaces, right? You can think about it this way. So probing is interesting. Probing is data dependent. This is one thing that you need to take into account. We process, in weight spaces, we process functions, not evaluations of functions. And at least theoretically, we show that we can learn how to probe, which is nice. But yeah, there are certain cases in which you want to learn on the function itself, for example, the INRs. And there are certain cases in which you want to learn on a specific data point being evaluated by the function, for example, for hallucination detection, right? So I think about it as complementary things.
Thank you.
Yeah, it's a great work, very inspiring. So I have two questions. The first question about the hallucination. So why do you select the attention map as the input instead of the MLP layer? Because as far as I know, MLP layer actually captures more facts. So yeah, is there any hypothesis like the attention is a major reason of the hallucination?
So we actually have 3 works in this direction on hallucination detections. Each one of those kind of tackles a different data type. So the first one worked on the output distributions. And this gives you kind of a gray box setup in which you don't need to go into the internals of the model and you can still say things. And then we try to work on activations. So we have the activation tensor approach. And the last thing that we did is to work on the attention maps, but you can actually think about the activations themselves, like the values of those activations, as node features. So this method kind of doesn't look only on the attention, it also looks on the activations, and you kind of have a general approach that encapsulates all the different data types that you have inside the model.
I see. The second question. So you talked about a lot of work about predicting the performance using neural architecture as a graph or some symmetric structure. So do you have any work using such technology to edit the model? I know the last work may be related, but it's not directly editing. It's just an approximation of the gradient. So do you have any work like directly predicting how should I edit the model?
Yeah, so many papers have preliminary experiments in this direction. We had some, we did some experiments on domain adaptation. Other people did stuff like pruning the neural network, which is an interesting editing task. I should say that we are pretty much in the beginning of the exploration of those directions. But yeah, people are working on that for sure.
Thank you.
Any other questions?
Thank you for the talk. It was very interesting. So one thing that seems like an obvious application to me when looking at the weights or the gradients would be to learn to explain the models. I don't think you mentioned this application in the talk, or I missed it. Is that not something that has been done yet?
Not yet.
Okay.
At least not public. Yeah, but I agree that this is a great direction and yeah, very natural to explore.
Thank you for your talk. I have two questions. The first is you talk about a lot of symmetries on different artifacts like the MLP weight and the attention map. And they have different symmetries like for MLP, there's permutation, and for attention maps, there's different things. So I wonder like how you identify those symmetries on different artifacts because this modality is not very intuitive compared to image. So this is like one of my confusion. And the second question is, do you think like the work on the weight space could be extended to like model distillation? So for example, you're taking a large language model artifacts and you train something and you can like from there you derive a distilled model, something like that?
Yeah, so I will first answer the second for sure. Yeah, this is definitely something we've been thinking about it. We didn't do it yet, but yeah, distillation is definitely something that can be done with this. Regarding the first question, it was how do you identify the symmetries, right? So I think in many cases this is kind of simple. In other cases, you just, think about the way you use those things and you see it. So for example, we started with permutation symmetries for MLPs, but if you use ReLUs, you actually have scaling symmetries. You can multiply by some scaling factor outside inside the parentheses, and then you essentially get the same function. So, we are kind of exploring this and, learning about new symmetries as we go. Truth is that for ReLU MLPs, in certain cases, you can actually show that those are the only symmetries, which is nice. But yeah, you can think about your input and you need to come up with the symmetries. This is a part of our work.
Okay, thank you.
Well, thank you so much for the great talk. And now now we have a 1 hour lunch break. So if you haven't collected the lunch cards, please go to our registration table and we will come back for a poster session on the right-hand side here. Thank you so much for the great talk.
Thanks.